Humanity's fastest machine could cross the entire Atlantic Ocean in under 30 seconds. And if you pointed that same machine at a single light year and waited, it would barely move at all. Hello, and welcome to Somniora Mind. I'm glad you're here. Tonight we're taking a single, deceptively simple unit of distance, the light year, and slowly, patiently discovering just how enormous it actually is. Not through more numbers thrown at you faster than they can settle, but gently, one comparison at a time, until the true scale of it has a chance to actually sink in before sleep finally arrives. Before we drift into that, 3 quiet questions to hold loosely tonight, the way you'd hold something you're simply curious about rather than trying to solve. First, if light itself takes a full year to cross this distance, how long would it take the fastest thing humanity has ever built? Second, is a light year mostly empty or mostly full of things worth passing on the way? Third, once you've traveled an entire light year, have you actually gone anywhere significant at all by the universe's own standards? We'll return to each of these before the night is through. For now, just let them settle, unhurried, somewhere in the back of your mind. A brief note before we begin. Some of tonight's numbers come from careful, well-confirmed measurement. Others are closer to reasonable, honest estimates, since even our best instruments can only measure certain distant, faint corners of space so precisely. I'll try to keep that distinction clear as we go. If these slow, quiet hours have ever helped you drift off, the kindest thing you could do is pass this along to someone else who might need a gentle night too. It costs nothing, and it helps this reach the next tired mind out there. One quiet mind at a time. There's nothing left to do now but let go. Let your body settle heavier into the mattress. Let your breathing slow on its own. You don't need to remember a single number from tonight by morning. Just let the distances drift past, soft and unhurried, growing larger and larger until they stop meaning anything except quiet and vast and far. Let's begin with the fastest thing we've ever built. Somewhere out past Mercury's orbit right now, a small spacecraft is moving faster than anything human hands have ever built, fast enough to cross the entire Atlantic Ocean, the whole stretch between Madrid and New York, in less time than it takes to read a short text message. This is the Parker Solar Probe, launched by NASA in 2018 and designed to swoop repeatedly through the Sun's outer atmosphere, drawing closer with each pass. To survive those close approaches without being pulled apart or burned away, it has to move extraordinarily fast, and at its closest points to the Sun, gravity itself accelerates it to speeds exceeding 600,000 kilometers per hour, a genuine record for anything humanity has ever constructed. At that speed, an ordinary commercial flight's 8-hour crossing of the Atlantic would take the probe well under 30 seconds. It's worth sitting with that number for a moment, because it represents something close to the practical ceiling of what human engineering can currently achieve, at least for something still recognizably built, launched, and controlled from Earth. No bullet, no rocket, nothing shaped by human hands has ever moved faster. In a very real sense, the Parker Solar Probe is the fastest anything humanity has ever managed to be. And yet, here's where tonight's whole exploration actually begins. Point that same record-breaking probe at a single light year of distance, and let it travel continuously at its peak recorded speed, and it would still take somewhere on the order of 1,500 years just to cross that one unit of distance. Not the width of the galaxy, not the distance to another star system. Just one light year, a distance so casually mentioned in astronomy that it's easy to forget how genuinely staggering it actually is. The question tonight isn't really how fast we are. It's what kind of distance is capable of making our very best effort look like it's barely moving at all. A light year sounds, to most ears, like a unit of time, something you might casually confuse with a calendar year or a stretch of waiting. It isn't. A light year is a distance, and a specific, precisely measured one at that. The total distance light itself travels across a full year, moving at its own, fixed, unchanging speed. This confusion is understandable and genuinely common, since the word itself blends a unit of time, the year, with something that sounds like it should describe duration rather than length. But once you strip away the confusing name, the underlying idea is fairly simple. Light moves at a constant, extraordinarily fast speed, roughly 300,000 kilometers every single second. Multiply that speed by the number of seconds in a full year, and you get a single, fixed distance, one so large that astronomers found it more convenient to use as a unit of measurement than to keep writing out an unwieldy string of zeros every time they wanted to describe how far away something truly distant actually was. That distance comes out to roughly 9.46 trillion kilometers, a number large enough that the mind tends to slide right past it without actually absorbing what it represents. It helps, a little, to break it down piece by piece. Light travels fast enough to circle the entire Earth about 7.5 times in the time it takes you to snap your fingers. Keep that exact pace going, without ever slowing down, for an entire year, and the total ground covered is one single light year. It's a genuinely strange unit once you notice what it's actually built from, tucked quietly into the closing thought of this particular fact. Astronomers didn't invent the light year because they were interested in describing time at all. They invented it because ordinary units of distance, kilometers, miles, even the width of entire countries, simply stopped being useful once the distances involved grew large enough to require something built directly from the speed of light itself. For nearly the whole of human history, almost no one suspected that light took any time at all to travel anywhere. Light out and light seen always felt like the same instant, the same simultaneous flash, with nothing in between worth measuring. This assumption held firm until 1676, when a Danish astronomer named Ole Romer noticed something quietly strange while carefully timing the eclipses of Io, one of Jupiter's 4 largest moons, as it slipped in and out of Jupiter's shadow with impressive, clock-like regularity. Romer noticed that these eclipses didn't always arrive exactly on schedule. When Earth was moving farther away from Jupiter in its own orbit around the Sun, the eclipses appeared to run slightly late. When Earth was moving closer to Jupiter instead, they appeared to run slightly early. Io itself wasn't misbehaving. Something about the distance between Earth and Jupiter was affecting how long the light announcing each eclipse actually took to arrive. Romer had, without quite intending to, become the first person in recorded history to demonstrate that light has a genuine, measurable speed, rather than crossing any distance instantly and immediately. His original estimate for that speed, calculated using the comparatively crude astronomical measurements available in the 17th century, wasn't perfectly precise, but it was remarkably close to correct, and it represented a genuine, foundational turning point in how physics would come to understand light from that moment onward. It's worth pausing on how quietly radical this discovery actually was, tucked into the closing thought of this particular fact. For the entire span of human history up to that point, the sky above every single person who had ever lived was assumed to be showing them the present moment, instantly and completely. Romer's careful, patient observations of a small, distant moon quietly proved otherwise, revealing for the first time that looking upward has always meant looking, at least a little, into the past. Light moves at roughly 299,792 kilometers every single second, a number so precisely, consistently measured that it's now used to define the length of a meter itself, rather than the other way around. For most of the 20th century, the speed of light was something physicists worked hard to measure as accurately as possible, using increasingly refined experimental techniques to narrow down its exact value. By 1983, that measured value had become so extraordinarily precise and consistent that an international body overseeing scientific units made an unusual decision. Rather than continuing to measure the speed of light using an independently defined meter, they flipped the relationship entirely, officially defining the meter itself as the distance light travels in a tiny, fixed fraction of a second. The speed of light became, in a sense, fixed by definition, precisely because it had already been measured so reliably that defining it this way made every other related measurement more consistent and precise as a result. This fixed, unchanging speed plays a foundational role in physics well beyond simply measuring astronomical distances, discussed on a previous night together in connection with relativity and the strange behavior of time near the speed of light. But for tonight's purposes, its significance is more direct and more grounded. Every single light year, every measurement of distance built from this constant, traces back to this one, remarkably precise, remarkably dependable number, the same steady speed governing everything from a flashlight beam crossing a bedroom to starlight finally arriving after a journey lasting centuries. It's a small, quietly elegant thing to sit with tonight. The very unit used to describe the vast, almost incomprehensible distances separating stars is built entirely from something extraordinarily small and fast, a single second's worth of travel, repeated, uninterrupted, for an entire year, adding up into a distance too enormous for the mind to hold all at once. Voyager 1, the spacecraft discussed on previous nights together in connection with its long journey beyond the solar system, is currently the most distant human-made object in existence, moving away from Earth at a genuinely impressive speed of roughly 61,000 kilometers per hour. And even at that speed, crossing a single light year would take it somewhere in the neighborhood of 17,000 years. It's worth letting that number actually settle for a moment, rather than sliding past it the way large numbers so often do. 17,000 years ago, human beings hadn't yet developed writing. Agriculture was only beginning to take shape in a small handful of scattered regions, and the last ice age hadn't fully released its grip on the planet. That's the length of time Voyager 1, moving continuously, without ever slowing down, would need just to complete a single light year of travel, a distance that represents only the very first, smallest measuring stick astronomers use for the space between stars. This isn't a limitation specific to Voyager, or a sign that its particular engineering fell short in some way. It's launched at a considerable speed for a spacecraft, faster than nearly everything else humanity has ever sent outward into the solar system, with the notable exception of the Parker Solar Probe discussed earlier tonight, which achieves its own extreme speed only briefly during close, gravity-assisted passes near the Sun, rather than sustaining that pace across an entire journey the way Voyager has continued to do for decades. There's a quiet, sobering honesty in comparing these two numbers side by side, tucked into the closing thought of this particular fact. Our fastest sustained spacecraft, humanity's most successful long-distance traveler, would need a span of time comparable to the entire rise of human civilization just to cross one single light year. And the nearest star beyond our own sun, as we'll discuss shortly, sits more than 4 times that distance away. Simply building a faster engine doesn't solve the problem of crossing a light year in any reasonable span of time, because the moment you add mass, fuel, supplies, and protection for an actual traveler, every genuine engineering estimate collapses right back down into centuries, no matter how clever the underlying propulsion technology happens to be. This is one of the more sobering, quietly important realizations tucked into any serious discussion of interstellar travel. It's tempting to imagine that pushing a probe or a spacecraft that much faster is simply a matter of better engines, more efficient fuel, or more advanced technology waiting somewhere in the future. But every additional requirement layered onto a real, crude, or heavily instrumented spacecraft, food, water, breathable air, radiation shielding thick enough to protect a human body across a multi-year or multi-decade journey, and physical armor capable of surviving collisions with even microscopic dust grains, which strike with the force of a small explosion at a meaningful fraction of light speed, adds enormous mass. And every added unit of mass requires dramatically more fuel to accelerate to any meaningful fraction of light speed in the first place, which itself adds further mass, in a genuinely difficult, compounding engineering problem that has never yet been fully solved, even on paper. This is part of why serious proposals for interstellar travel tend to focus on extremely small, extremely lightweight probes rather than anything resembling a crewed spacecraft. Projects like Breakthrough Starshot, a privately funded research initiative announced in 2016, have proposed accelerating gram-scale probes attached to thin, reflective sails using powerful ground-based lasers, aiming for speeds reaching perhaps 20% of the speed of light, fast enough, in principle, to reach the nearest star system in roughly 20 years rather than tens of thousands. Even this approach, genuinely serious and actively researched, remains firmly in early theoretical and small-scale testing stages, facing enormous unresolved engineering challenges of its own. It's a fitting, quietly humbling thought to hold on to tonight. The barrier standing between us and the stars was never really about the strength of our engines. It's the sheer, patient scale of the distance itself, a problem that no amount of raw thrust alone has ever been able to fully outrun. Here's the detail that tends to catch people off guard the most, tucked quietly into the middle of tonight's exploration. You could travel an entire light year outward from the sun, the full 9.46 trillion kilometers, and still, technically, remain within the outer edges of our own solar system. This comes down to the Oort cloud, a vast, thin, spherical shell of icy debris believed to surround the sun at an almost unimaginable distance, first proposed in 1950 by Dutch astronomer Jan Oort, after he noticed that certain comets arrived from directions and along orbits that couldn't be explained by anything closer in, within the solar system's more familiar, better mapped regions. Oort reasoned that these comets had to be coming from somewhere much farther out, a distant, largely unseen reservoir of icy material left over from the solar system's original formation, gently, loosely bound to the sun's gravity across an enormous, barely imaginable span of space. Current estimates suggest the Oort cloud's outer edge might extend somewhere between 1 and 2 light years from the sun, meaning that a spacecraft could travel the same 17,000 years discussed a little earlier tonight, the same 17,000 years Voyager 1 would need to cross a single light year, and still, quite possibly, remain within our own solar system's own extended gravitational neighborhood the entire time, never having genuinely departed into true interstellar space. At all. It's a genuinely strange thing to sit with tonight, tucked into the closing thought of this particular fact. An entire light year, The very same distance that makes our fastest spacecraft look practically motionless might still only represent a single step across our own solar system's outer yard, rather than any meaningful journey towards somewhere else entirely. The true distance separating us from another star system turns out to be considerably larger still. The nearest star beyond our own sun sits roughly 4.2 light-years away, meaning the light currently reaching Earth from it left its surface more than 4 years ago, and meaning any spacecraft attempting the journey using anything resembling current technology would need a span of time stretching well beyond 70,000 years just to arrive. This star is Proxima Centauri, a small, faint red dwarf star, part of a wider triple star system that also includes two larger, more sun-like stars called Alpha Centauri A and Alpha Centauri B, orbiting one another closely, while Proxima itself drifts in a much wider, more distant orbit around the pair. Proxima Centauri holds particular interest for astronomers partly because it's known to host at least one confirmed planet, called Proxima b, orbiting within a distance from its star that would, in principle, allow liquid water to exist on its surface, making it one of the more intriguing nearby candidates in the ongoing search for potentially habitable worlds beyond our own solar system. And yet, despite being our single closest stellar neighbor, genuinely reaching it remains firmly outside anything achievable with current or near-future technology. Using Voyager 1's own sustained speed as a rough benchmark, a spacecraft would need over 70,000 years, roughly 4 times the 17,000 years required for a single light year, just to complete the crossing. Even the considerably more ambitious, laser-propelled concepts discussed a moment ago, aiming for a meaningful fraction of light speed itself, remain entirely theoretical, tested so far only in extremely early, small-scale experimental stages. There's a particular kind of vertigo worth sitting with tonight, tucked into the closing thought of this fact. Proxima Centauri is, by an enormous margin, the closest star system to our own, out of the hundreds of billions scattered throughout our galaxy alone. And it remains, by any practical measure available to us today, entirely, comfortably out of reach. Astronomers rarely rely on the light year alone when measuring truly vast cosmic distances. Instead, they often reach for a related, if considerably less intuitive, unit called the parsec, one built not from the speed of light directly, but from the geometry of triangles and the gentle, yearly wobble of nearby stars against the more distant background sky. This method is called parallax, and it works on a principle you can test yourself with nothing more than an outstretched thumb. Hold your thumb at arm's length and close one eye, then the other, and notice how your thumb appears to shift slightly against the background behind it, even though your thumb itself never actually moved. That apparent shift happens because your two eyes are viewing your thumb from two slightly different positions. Astronomers use exactly the same basic principle, except instead of two eyes, they use Earth's own position on opposite sides of its orbit around the Sun, 6 months apart, measuring the tiny, precise apparent shift of a nearby star against the much more distant, essentially fixed background of far more distant stars behind it. The size of that tiny apparent shift reveals the star's actual distance through simple, reliable geometry, and a parsec is defined as the specific distance at which a star would show an apparent shift of exactly 1 arcsecond, an extremely small angle, using this particular method. 1 parsec works out to be roughly 3.26 light-years, meaning Proxima Centauri, discussed a moment ago, sits at a distance of only about 1.3 parsecs, a genuinely close distance by the standards professional astronomers typically work with. It's a fitting, quietly elegant detail to add to tonight's exploration. Even the light year, already almost too large a distance for the mind to properly hold, isn't always the most convenient unit available. Astronomers routinely reach for something built instead from simple, patient geometry, the same basic principle behind an outstretched thumb, scaled up to measure some of the most distant, most carefully confirmed distances in the entire observable universe. A single light year, however enormous it might feel by any human standard, turns out to be a genuinely tiny unit once you start comparing it against the scale of our own galaxy, let alone the universe beyond it. The Milky Way, our own home galaxy, discussed on a previous night together, spans somewhere around 100,000 light years from one edge to the other, meaning the single light year occupying so much of tonight's attention represents only about 100,000th of our galaxy's total width, a fraction so small it barely registers as anything at all against the galaxy's true scale. Our solar system itself sits roughly 26,000 light years from the galaxy's own crowded, energetic center, a distance that would take Voyager 1, moving at its own sustained pace discussed earlier tonight, somewhere in the neighborhood of 450 million years to complete. And the Milky Way itself, despite containing hundreds of billions of stars and stretching across that 100,000 light-year expanse, is only one galaxy among an estimated hundreds of billions of others scattered throughout the observable universe, a topic explored more fully on a previous night together in connection with the true edge of everything we can see. Andromeda, our nearest large galactic neighbor, discussed on that same previous night, sits not a handful of light years away, and not even a few 100,000, but over 2 million light years distant, a gap so much larger than anything covered so far tonight that it becomes genuinely difficult to hold both scales in mind at the same time. It's worth sitting with that contrast gently before drifting further into tonight's exploration. The single light year that made our fastest spacecraft look practically frozen in place, the same distance that still leaves us technically inside our own solar systems or cloud, is, from the galaxy's own perspective, essentially nothing at all, a single, barely noticeable step within a structure so much larger that the difference in scale stops being something the mind can meaningfully compare at all. If a spacecraft genuinely could travel close enough to the speed of light, something remarkable would happen to its crew's own experience of time, one that would make certain otherwise impossible journeys feel, from the traveler's own perspective, considerably shorter than they would appear to anyone watching from Earth. We explored this in detail on a previous night together, in connection with relativity and the strange, genuine slowing of time experienced by anything moving at a significant fraction of light speed, confirmed through real experiments involving fast-moving particles and precise atomic clocks. The same basic effect would apply to any spacecraft capable of reaching a meaningful fraction of light speed, though achieving that speed in the first place remains, as discussed earlier tonight, an entirely separate and still unsolved engineering challenge of its own. A crew traveling at 90% of light speed, purely as an illustrative example, would experience time passing considerably more slowly than an observer who stayed behind on Earth, meaning a journey that takes many years according to Earth's own clocks might feel, to the traveling crew themselves, like only a fraction of that duration had actually passed. This doesn't solve the practical engineering problems discussed earlier tonight, the enormous fuel requirements, the radiation shielding, the sheer mass involved in protecting and sustaining an actual human crew across such an extreme journey. But it does offer a genuinely fascinating theoretical possibility, worth holding on to gently even while everything else remains firmly out of reach for now. A sufficiently fast, sufficiently well-protected spacecraft might, in principle, allow its own crew to reach even fairly distant stars within a single human lifetime from their own personal experience of time, even while many additional years or decades passed for everyone and everything left behind on Earth. It's a fitting, quietly strange thought to add to tonight's exploration. Distance and time, so often treated as two separate, independent measurements, turn out to be more deeply intertwined than ordinary experience would ever suggest, offering, at least in careful theory, a small, narrow doorway through which some of tonight's otherwise impossible distances might, for the traveler alone, feel considerably more forgiving. Before the Parker Solar Probe and Voyager 1, discussed throughout tonight, humanity's fastest achievements looked considerably more modest, a steady, patient progression stretching back across less than a century of powered flight and spaceflight combined. The Apollo missions of the late 1960s and early 1970s, carrying astronauts toward the moon and back, reached speeds of roughly 40,000 kilometers per hour during their return trips to Earth, propelled by nothing more exotic than Earth's own gravity pulling them back in during re-entry, and they held records for the fastest human crewed travel for decades afterward. The Helios probes, launched in the mid-1970s to study the Sun at closer range than anything before them, reached speeds of around 250,000 kilometers per hour during their closest approaches, quietly setting new benchmarks for uncrewed spacecraft that would stand for decades before eventually being surpassed. Each of these milestones represented, at the time, close to the absolute limit of what careful engineering and available technology could achieve, exactly the way the Parker Solar Probe represents that same limit today. And each was eventually surpassed, not through some single, dramatic breakthrough, but through decades of steady, incremental refinement, better materials, better trajectories, clever use of gravity assists from planets along the way, each small improvement building carefully on everything that came before it. It's a fitting, quietly hopeful thought to hold on to tonight, tucked into this brief look back at how we arrived at our current fastest achievement. Progress toward genuinely vast distances has never come from a single, sudden leap. It's come from patient, steady refinement, one careful improvement after another, the same unhurried, incremental process quietly continuing today, even while the light year itself remains, for now, as vast and as humbling as it has always been. The space filling a single light year isn't the crowded, star-studded expanse popular illustrations often suggest. It's overwhelmingly, almost perfectly empty, holding vastly more nothing than anything else at all. Interstellar space, the region between star systems, contains an extremely thin scattering of gas and dust, often no more than a handful of atoms in every cubic centimeter, a density so low that it counts as a better vacuum than almost anything achievable inside a laboratory here on Earth. Within a single light year of empty space, the total amount of solid matter you'd actually encounter, spread across that entire trillion-kilometer stretch, would be almost negligible compared to the sheer volume of space it occupies, a whisper-thin scattering of individual atoms and dust grains, drifting slowly through what is, for all practical purposes, a vast, silent, nearly perfect emptiness. This helps explain something discussed a little earlier tonight, in connection with the dangers facing any spacecraft attempting to travel at extreme speed. It isn't that interstellar space is densely packed with hazards waiting to be struck. It's that any given hazard, however rare, becomes genuinely dangerous specifically because there's so little else around to have already slowed it down or deflected it away, and because a spacecraft moving at a meaningful fraction of light speed would be covering so much distance so quickly that even a very rare, very sparse scattering of dust still adds up to a real, if infrequent, collision risk over the course of a multi-year journey. It's a strange, quietly peaceful thought to hold on to tonight. The single light year that has occupied so much of this exploration isn't filled with looming obstacles, dramatic asteroid fields, or crowded, busy traffic the way certain films might suggest. It's mostly just still, patient, undisturbed emptiness, stretching on, with only the faintest, most occasional scattering of anything solid at all breaking up that vast, quiet nothing. Before it slipped permanently beyond the reach of any camera, one particular spacecraft was turned around one final time, aimed not outward into the darkness ahead of it, but back toward the small, pale world it had left behind years earlier. This was Voyager 1, discussed throughout tonight, and in 1990, at the request of astronomer Carl Sagan, NASA agreed to rotate the spacecraft's cameras for one last look homeward before they were powered down permanently to conserve the spacecraft's remaining energy for its long journey ahead. From a distance of roughly 6 billion kilometers, far beyond the orbit of Neptune, Voyager 1 captured an image showing Earth as a single, faint, nearly invisible point of light, a fraction of a single pixel wide, easily missed entirely by anyone who didn't already know exactly where to look for it. Sagan later wrote about that image in words that have stayed with people for decades since, describing that pale, barely visible point of light as home to everyone who has ever lived, every joy and every hardship, every civilization that ever rose and fell, all of it contained within that single, nearly invisible speck, suspended, in his words, on a mote of dust caught in a sunbeam. It's worth returning to that image tonight, tucked gently into this particular stretch of tonight's exploration, because it offers something the raw numbers alone rarely manage to capture. Every distance discussed so far tonight, the single light year that dwarfs our fastest spacecraft, the Oort cloud stretching even farther still, Proxima Centauri sitting more than 4 times farther beyond that. All of it begins from that same small, pale point of light, a single quiet home, tucked into an otherwise vast, patient darkness. Reaching even the very edge of our own solar system, let alone another star entirely, has only become possible within the lifetime of people who might, right now, be listening to this. Voyager 1, discussed throughout tonight, crossed the heliopause, the boundary separating our sun's direct influence from true interstellar space, in 2012, 35 years after its original 1977 launch. It remains, even now, the only human-made object to have genuinely left the region dominated by our sun's own solar wind, a milestone that took decades of patient, uninterrupted travel to achieve, even while covering a distance that, as discussed earlier tonight, still amounts to only a small, early fraction of the single light year occupying so much of tonight's attention. Before Voyager, no human effort had ever reached anywhere close to that boundary, and it's worth remembering that the entire history of powered space travel, from the first satellite launched in 1957 through to Voyager's own historic crossing, spans considerably less than a single century. A genuinely brief stretch of time compared to the thousands or tens of thousands of years discussed throughout tonight's exploration of what it would actually take to cross even a single light year, let alone reach another star. There's a fitting, quietly hopeful thought tucked into that timeline, worth carrying gently into the rest of tonight's exploration. Everything covered so far, the vast, humbling distances, the centuries and millennia required, the sheer emptiness stretching between here and anywhere else, has all been discovered, measured, and confirmed within a stretch of time barely longer than a single human lifetime. Whatever comes next, whatever incremental progress continues quietly building on everything covered tonight, is still, by any reasonable measure, only just beginning. Before wrestling with something as vast as an entire light year, it helps to start considerably smaller, with a distance the mind can actually hold on to. The roughly 8 minutes and 20 seconds it takes sunlight to reach Earth. This means the sun you might glimpse through a window during the day never actually shows you the sun as it exists in that exact moment. It shows you the sun as it existed a little over 8 minutes earlier, the length of time its light has spent crossing the roughly 150 million kilometers separating the sun from Earth. If the sun somehow vanished entirely, right now, this instant, Earth would continue receiving its light and warmth for another 8 minutes and 20 seconds, completely unaware, before anyone noticed anything had changed at all. Moonlight offers an even smaller, gentler starting point still. The reflected sunlight bouncing off the moon's surface takes only about 1.3 seconds to reach Earth, a delay so brief it's genuinely impossible to notice without precise instruments, yet still a real, measurable stretch of time, the same basic principle scaled down to something almost intimate in size. Even the flash of a lightning bolt witnessed from a few kilometers away arrives with its own tiny, genuine delay, vanishingly small, but built from exactly the same underlying physics responsible for the 8-minute delay of sunlight, and the far more staggering delays discussed throughout the rest of tonight. It's worth holding on to that small, human-scale starting point for a moment before drifting back into tonight's larger distances. 8 minutes for the Sun, a little over 4 years for Proxima Centauri, discussed earlier tonight. Thousands, and eventually millions, of years for the distances still to come. Each step outward multiplies the last by an almost dizzying factor, and yet each one traces back to the very same simple, dependable rule: light moving at its own fixed, unhurried pace, patiently carrying its message across whatever distance happens to lie in front of it. Stars appear as tiny, faint points of light in the night sky, indistinguishable from one another in size to the naked eye, not because they're actually small, but because the light year itself is so enormous that even genuinely massive objects shrink down to almost nothing once you place them far enough away. This comes down to a straightforward, well-understood principle called the inverse square law, which describes how the brightness of any light source fades rapidly as distance increases, dropping off with the square of the distance involved. Double the distance to a light source, and it appears only a quarter as bright. Multiply the distance by 10, and it appears 100 times fainter. Stretch that distance out across multiple light years, the standard spacing between neighboring stars in our own galactic neighborhood, and even a star considerably larger and more luminous than our own sun fades down into a faint, easily overlooked point of light, visually indistinguishable from countless smaller, dimmer stars that simply happen to sit closer to Earth. This is part of why the night sky can be genuinely misleading if taken at face value. A particularly bright-looking star might be relatively small and unremarkable, but simply close by, in relative astronomical terms. A far larger, far more luminous star might appear considerably fainter, or even go unnoticed entirely, purely because it happens to sit many additional light years farther away. Untangling a star's true size and brightness from its mere apparent brightness in the sky requires knowing its actual distance, which is exactly why the parallax method discussed a little earlier tonight plays such a foundational role in modern astronomy. There's something quietly humbling in that distinction, tucked into the closing thought of this particular fact. The night sky isn't showing you the universe's true, relative scale at all. It's showing you a carefully, if unintentionally, distorted picture, one where genuine size and true distance have both been quietly flattened down into nothing more than a single, faint point of light, with a light year's worth of separation, or many light years more, doing almost all of the flattening. Every time you glance upward at a clear night sky, you're not looking at the universe as it exists right now. You're looking at an enormous, overlapping collage of different moments, each star showing you a slightly different slice of the past, depending entirely on how many light years its own light has had to travel to finally reach you. A star sitting 4 light years away shows you light that left its surface 4 years ago. A star sitting 400 light years away shows you light that left 4 centuries ago, long before most current technology, and in some cases entire nations, existed at all. Look toward a sufficiently distant galaxy, and the light arriving tonight may have left its source before human beings had developed writing or agriculture, or, in the most extreme cases discussed on a previous night together, before Earth itself had even finished forming. This means the night sky isn't really a single, unified snapshot at all, despite how effortlessly it appears that way to the naked eye. It's closer to a vast, layered composite, with the light from every visible object carrying its own separate, independent age, all of it arriving together at the very same moment, purely by coincidence, simply because that's the moment you happen to look upward and notice it. 2 neighboring points of light in the sky might be showing you moments separated by hundreds or even thousands of years, layered directly on top of one another with no visible seam between them at all. It's a quietly beautiful thing to hold on to tonight, tucked gently into this stretch of the exploration. Every night sky you've ever looked up at was never really a single moment in time. It was always an enormous, patient collage, built from countless separate pasts, all arriving together, gently, at exactly the moment you happened to be there, looking upward, ready to receive them. Within just 10 light years of Earth, a modest, easily countable neighborhood by the standards of an entire galaxy, sit fewer than a dozen known star systems, a genuinely small, sparse gathering once you consider how much space that 10-light-year bubble actually contains. This nearby collection includes familiar names like Sirius, the brightest star visible in Earth's night sky, sitting roughly 8.6 light-years away, along with smaller, fainter red dwarf stars like Barnard's Star and the Alpha Centauri system discussed earlier tonight, home to Proxima Centauri at that comparatively close 4.2 light-year distance. Expand the search out to 20 light-years, and the count grows only modestly, adding a few dozen more systems. Still a remarkably sparse gathering considering the sheer volume of space contained within a sphere 20 light-years across. This sparseness offers a genuinely useful, grounded way of appreciating just how empty our own corner of the galaxy actually is, tucked alongside everything else discussed tonight about the emptiness of interstellar space itself. Our sun isn't nestled into some densely packed, crowded stellar neighborhood, jostling for space among countless close neighbors. It sits instead in a comparatively quiet, sparsely populated region, with its very nearest neighbor, as established earlier tonight, already representing a distance well beyond anything achievable with current technology. It's worth sitting with that sparseness for a moment, tucked into the closing thought of this particular fact. Even setting aside every engineering challenge discussed throughout tonight, simply having somewhere nearby worth traveling to is itself a genuinely limited proposition. The handful of stars within a reasonable, if still staggering, distance of Earth represent nearly the entirety of what current human technology could ever hope to seriously consider reaching. A short, sparse list drawn from a galaxy containing hundreds of billions of stars in total. A small number of physicists have spent real, careful effort exploring a genuinely strange theoretical loophole, one that wouldn't require moving faster than light at all, but might, at least on paper, allow a spacecraft to reach a distant star in a dramatically shorter time than anything discussed so far tonight, by reshaping the space around it instead of racing through it directly. This concept is called an Alcubierre drive, named after physicist Miguel Alcubierre, who proposed it in 1994 as a mathematically valid, if wildly impractical, solution within the framework of general relativity. The same theory discussed on previous nights together in connection with gravity, black holes, and the curvature of spacetime itself. The basic idea involves contracting space directly in front of a spacecraft while expanding space behind it, creating a kind of traveling wave or bubble in spacetime itself, one that would carry the spacecraft along within it, all without the spacecraft ever needing to move faster than light relative to the space immediately surrounding it, technically respecting the same fundamental speed limit discussed throughout tonight, even while achieving an effective speed relative to the wider universe outside that bubble that could, in principle, exceed it. It's important to be genuinely clear about where this idea currently stands, tucked appropriately among tonight's more speculative territory. Alcubierre's original proposal, much like the wormholes and exotic matter discussed on a previous night together, requires a form of matter or energy with genuinely unusual properties, sometimes called negative energy, that has never been confirmed to exist in any usable, meaningful quantity. And some theoretical analysis since Alcubierre's original paper has suggested the energy requirements involved might be so extreme as to be permanently, physically unachievable, regardless of any future advances in engineering or technology. Still, it remains a genuinely fascinating thought to add near the end of tonight's exploration. Even within the same trusted equations responsible for accurately predicting black holes, gravitational waves, and the bending of starlight, there remains at least a small, mathematically valid door left slightly ajar, one suggesting that reaching another star might not always require a faster engine at all, but might instead simply require learning, someday, how to gently, carefully reshape the space in between. A giant, aging star sitting roughly 640 light-years away could have already exploded completely and catastrophically at some point within the last several centuries, and Earth would have absolutely no way of knowing about it until that light finally, patiently completes its journey here. This star is Betelgeuse, a massive, red supergiant marking one shoulder of the constellation Orion, and one of the closer examples of a star nearing the natural end of its life, expected, at some point, to end in a genuine supernova, one of the most energetic events discussed on a previous night together. Because Betelgeuse sits roughly 640 light-years away, the light reaching Earth tonight left its surface around the time of the early Renaissance in Europe, showing us the star not as it exists right now, but as it existed centuries ago, exactly the same layered, delayed view of the night sky discussed a little earlier tonight. This means Betelgeuse could, in principle, have already exploded at almost any point within roughly the last 6 centuries, and there would be absolutely no way for anyone on Earth to know about it yet, since the light announcing that explosion is still, patiently, making its way across the same vast distance discussed throughout tonight. In 2019, astronomers noticed Betelgeuse dimming unexpectedly, sparking brief, excited speculation that the long-anticipated supernova might finally be underway. Careful follow-up observation eventually determined the dimming was caused by an enormous cloud of dust the star itself had ejected, temporarily blocking some of its light, rather than any sign of imminent collapse. but the excitement surrounding that brief false alarm offered a genuinely vivid, real-world reminder of exactly the delay discussed throughout tonight's entire exploration. It's a strange, quietly thrilling thought to hold on to near the end of tonight's journey. Somewhere above you, whenever you next happen to glance upward, a star's eventual, inevitable ending may already be fully underway. Its light simply still patiently completing a centuries-long journey to finally deliver the news. A famous line from a well-loved science fiction franchise once boasted about completing a dangerous smuggling route in under 12 parsecs, casually treating a unit of distance as though it were a measure of time instead, a mistake that has quietly amused astronomers for decades since. The line comes from the original Star Wars film, released in 1977, in which the character Han Solo boasts that his ship, the Millennium Falcon, made a particular smuggling route in less than 12 parsecs, a description that only makes sense if you mistake a parsec, the unit of distance discussed earlier tonight, for a unit of time instead, since bragging about completing a route in a shorter distance doesn't actually say anything meaningful about how fast a ship traveled it. Various explanations have been proposed since, some offered gently after the fact by writers and fans alike, suggesting the route might have involved a shorter, more dangerous path through hazardous space, one that most pilots avoided, making the shorter distance itself the impressive, boast-worthy achievement rather than any claim about raw speed. Whether or not that explanation reflects the line's original intent, it remains one of the more famous, most enduring mix-ups between distance and time in mainstream popular culture. This confusion connects directly back to the very first correction offered at the start of tonight's exploration, the easy, understandable mistake of treating a light year or a parsec as some kind of measurement of duration rather than distance. It's a mistake common enough that even a wildly popular, carefully written film managed to include it, apparently without anyone involved in its production catching the error before release, and it has remained, warmly and good-naturedly, a small point of amusement among astronomers and careful science fiction fans ever since. It's a fitting, gently amusing note to add near the very end of tonight's exploration. Even after decades of careful astronomical measurement, and now, after an entire night spent carefully untangling exactly what a light year truly represents, the distinction between distance and time remains, for most people, an entirely understandable, remarkably easy thing to quietly, harmlessly get wrong. The parallax method discussed earlier tonight works beautifully for measuring nearby stars, but it quietly breaks down entirely once distances grow large enough. Since even the tiny, precise shift it depends on eventually becomes too small for any instrument to reliably detect. Beyond a certain point, astronomers have to rely on an entirely different, considerably more clever technique instead. This method relies on what astronomers call standard candles, objects whose true, intrinsic brightness is already known or can be reliably calculated, allowing their observed, apparent brightness as seen from Earth to reveal their distance through simple, dependable physics, the same inverse square law discussed a little earlier tonight in connection with why distant stars appear as such faint, tiny points of light. A particular type of pulsating star called a Cepheid variable proved especially useful for this purpose, since its brightness rises and falls in a very precise, predictable rhythm directly tied to its true, intrinsic brightness, discovered by astronomer Henrietta Leavitt in the early 20th century through careful, patient study of thousands of these stars. By measuring how quickly a distant Cepheid variable's brightness cycles up and down, astronomers can calculate its true, intrinsic brightness, and by comparing that true brightness against how faint it actually appears from Earth, They can calculate its distance with remarkable reliability, even at distances far too vast for the parallax method discussed earlier to have any hope of working at all. This technique, and others built on similar principles, extended astronomers' reach dramatically, allowing distances to be confidently measured not just across nearby stars within our own galaxy, but out across other galaxies entirely, playing an essential, foundational role in the discoveries discussed on a previous night together, including the accelerating expansion of the universe itself. It's a fitting, quietly elegant note to add near the close of tonight's exploration. Even once simple, direct geometry runs out of reach, astronomers have continued finding new, patient, clever ways of coaxing genuine distance out of nothing more than careful, sustained observation, extending our understanding of scale far beyond anything a single, straightforward measurement could ever have managed on its own. Let's return, gently, to the three questions from the very start of the night. If light itself takes a full year to cross this distance, how long would it take the fastest thing humanity has ever built? Centuries, at the very least. Even at a record-breaking speed, no human-made object has ever sustained for more than a brief, gravity-assisted moment. Is a light year mostly empty, or mostly full of things worth passing on the way? Overwhelmingly empty. It turns out, a vast, quiet, near-perfect vacuum, with only the faintest scattering of dust and the occasional, distant edge of an icy cloud to interrupt it. And once you've traveled an entire light year, have you actually gone anywhere significant by the universe's own standards? Barely. Possibly not even far enough to leave your own solar system's outer yard, let alone reach another star entirely. There are really only two honest ways to sit with everything covered tonight. One is to let the scale of it settle into something like quiet acceptance. This small solar system, this one pale, fragile home, being enough, simply because it's the one we actually have. The other is to feel that same scale and keep reaching anyway, sending small, careful, patient signals outward regardless, a golden record, a probe, a photograph of a pale blue dot, not because any of it is likely to be answered, but because something in us has never quite been able to stop trying. You don't need to decide between the two tonight. Both are honest responses to the very same vast, quiet distance, and there's no wrong way to hold something this large. Whichever one feels truer to you right now, let it settle gently, without needing to be resolved before sleep arrives. So let yourself rest now, the way starlight rests briefly on your skin after traveling farther than the mind can properly hold. There's nowhere left to travel tonight, and nothing left to measure. Just this room, this breath, and the quiet, patient dark outside, exactly as far away and exactly as close as it has always been. Thank you for spending these hours here, in Somniora Mind, one quiet mind at a time. Rest now. You've earned it. Good night.